Yeah, so to understand the word external, we will just talk about the letter M over there. That is mass. Mass of what? If you have a rigid body, which will be the case most of the time, then we don't have to worry much. But then, suppose this is a box, and or say this is a cart. Now there is a human being in the cart, and the human being is trying to push the cart towards the back. Now, will he be able to move the cart? There is no friction on the ground. Will he be able to move the cart? He will not be able to move the cart. This constitutes a internal force. Why will he not be able to move the cart? Let me show you. He is pushing the cart over here with F force. So why does the cart not move? If I had standing from outside, a man pushes the cart with F force, the cart is going to move. From inside, if I push, it is not going to move. So if I am pushing from inside, it's not going to move. Why? The cart got a force. The cart had a mass, say M. This cart had a mass, say M. The man had a mass, say small m. So I'm just looking at the cart. So why is the cart not moving? Because to push it, the man has got a grounding over here, and with his foot he is pushing the cart back also, with an equal and opposite force. How am I so sure it is equal and opposite? Why am I so sure it is equal and opposite? Because I'll study the man also separately. I wanted to give you an easier example, but anyhow, this will be a good one for you. Please try to understand it well. Now, we have discussed that the third law of motion is valid when I push something, that thing pushes me back with the equal and opposite force. So here I am not very sure of this force is same as that force or not. What is this force? The man pushing the cart with a certain force, F. This, the man pushing the cart back with the foot. With the foot, the man is pushing the cart back this way, so that he can have a grounding on the cart with which he pushes. Now suppose the man was on roller skates. He won't be able to push over here. Why he won't be able to push? You can try yourself. The guy will just slip. If he was on roller skates, he will just slip. He has to groove his leg somewhere, or he has to have some friction on the ground with the help of which he is going to push. So in fact, this force is related to that force. What I am saying is this force will be equal and opposite to that force. This force will be same as that force. F is going to be same as F dash. Why am I so sure? I am going to study the man. Now man pushes the cart with F. The cart pushes the man back with F on the hand. The cart pushes man back with F. That is for sure, right? Because that is action and reaction at the point of contact on the two different bodies, as discussed earlier. Now, this man pushes the cart back with F dash, hence the cart pushes his leg forward with F dash. That's also action reaction. That is how you walk on the ground. That is how you walk, I hope you know. This is your ground, and you push the ground back, the ground pushes you forward. You push the ground back, the ground pushes you forward. The ground doesn't go back, but you go forward. With your push, the ground is not going back, not in the sense you can see it, and you go forward. You get a force equal and opposite in the forward direction, hence you go forward. It is friction which is helping you over there. So when we are discussing friction, I'll be discussing that in a little more detail, but for now let's have it that you pushed the ground back and the ground pushed you forward. You pushed it back with F dash, that is your F dash over here, and it pushed you forward with F dash. Now on you, what are the forces? This is U, and what are the forces on you? F from here and F dash from there. Now you are not going anywhere. You are just over there, you are not going anywhere. It is not like you push the cart and the cart is going back, and if you were going back along with it, your acceleration will be forward and F dash will be more than F. And if F dash is more than F, then the cart would be going that way. So that is impossible case. That means you are going through the wall. You are going forward and the cart is going back. That is you can't even, that's bizarre. You can't even imagine that. So I'll repeat that. What is bizarre, I'll repeat. So you have to think over it. It's a good thing to just analyze the case. It's a very simple case, but please do analyze. I am saying that if F was greater than F dash, I very well know F is equal to F dash. I'm saying if F was greater than F dash, then what weird thing would be happening? If F was greater than F dash, then you are going back. You are going this way because F is greater than F dash. That is, you are going back on the cart. You are going this way. And if F is greater than F dash, then the cart is going forward. That means the cart went forward and you went back. Cart came over here, you went back. So your contact, you're losing your contact. So you were thinking that you're giving a good force, F force, but then you're losing. Automatically you're making your force less. So by the way, this is very much possible. Like when you don't have enough friction, then what happens? The cart will go forward, you will go back. In that scenario, the whole center of mass is going to remain at the same spot. But then the bizarre case, what I was talking was, when F dash is greater than F. So I hope you understand, when F is greater than F dash, you guys will be separating out. You will be going back, cart will be going forward, and your push, you won't be able to push with that much amount, with that much vigor, because your separation would have increased, and ultimately your F is going to be, the new F is going to be new F dash, then new push over there. But in this case also, when the cart went forward and you went back, cart went forward, you went back, the center of mass remains at the same spot wherever it was. The center of mass doesn't go forward or back. We'll be discussing that center of mass in the next chapter. So if I consider your mass M and the mass of the cart totally as one body, then the center of mass has not gone anywhere. You guys have moved. I can agree to that. And the other case, the bizarre case, is when F dash is greater than F. Means, what was F dash? That friction force what you generated over here. If the friction force was greater than your push on the wall, if that was greater, then what happens? What happens? This cart has two forces, one forward, your push, and the friction. That exceeds, so the cart is going back. So the cart, this is a blue cart which is going back. And you are going forward. Why? Because F dash is more than F. If F dash is more than F, you are going forward. So that means you are going through the wall of the cart. You are going forward and the cart is going back. So that is a physical situation which you can imagine cannot happen. So in physics, you have to imagine such situations which are not going to happen and write or correct your equations accordingly. So what is happening over here is, if your footing was right and you were not slipping, if you are slipping, this is what happened. This is what happened. F was greater than F dash and the cart went forward a bit and you went back a bit, but the center of mass remained at the same place. But if your footing was right and you were pushing, then the cart did not move at all, you did not move at all. F is equal to F dash. If your footing is right, you did not move. I am very sure that you did not move. That means, studying your body, I came to know that F is equal to F dash, but those were the forces on the cart also, the same F and the same F dash. So on your body, if F is equal to F dash, then on the cart, F is equal to F dash. So you can imagine, if friction is too difficult for you to imagine, then you can imagine you're sitting on a seat and pushing the car forward. Well, by sitting on the seat, pushing the car forward, you're pushing forward with your hand, but your back is pushing the cart back. So that is internal force. So how much ever you apply, even the Hulk is inside the car, he will not be able to move the car. So to move it, you have to have an external force. If this is frictionless, then even a child outside will be able to push it. A Hulk is not required if it is frictionless. Even a 1 gram force, 2 gram force is going to push it. Imagine the cart in space, in deep space where there is no friction. If somebody is able to generate a push, And how will a person be able to generate a push if there is no friction outside? That's something different. You'll have conservation of momentum. You throw something back and something goes forward. You can have a gas propulsion or whatever. So if you are able to push, the whole thing is going to go forward. How much ever light the push is, with your little finger you can move a massive truck in deep space. So if you are able to generate that push. So, and that will happen. If you just push, the truck will go forward and you will go back. Center of mass of you and truck will remain same if you consider that much as a system. So the point over here is an internal force is not going to move it. So if the point is an internal force is not going to move the mass, you need to have an external force to move the mass. The body may have many bodies inside which are putting forces on each other, which is the truth with this, say, piece of duster also. There are a lot of molecules which are pushing each other. So that doesn't move this duster anywhere. This duster as a whole doesn't go in a Brownian movement, wherein all the molecules internally are going in. You need to have an external force on this to make it move which direction, whichever way you are pushing it is going to move in that direction. So you need to have an external force. And just to confuse you, let me give you a situation. Say this body had a elastic connection between them. This thing can extend. This is an elastic. If I put a force of F on this body, then what is what over here? Now if I consider this M1 and M2 as one body, then I can write the equation. F is the net external force on this total body of M1 plus M2, and this body will have an acceleration A, but that acceleration is of which part? Is that acceleration this acceleration? No. A is not equal to A2. What happens to this? This is, I think, almost standing where it was. It doesn't even move. So A1 is 0, A2 is something else. What is A? A is where this mass is. A is the acceleration of this mass. But where is this mass? Is this mass here? No, it is not. Is that mass here? No, it is not. That mass is somewhere in between. Depending on how much is the mass. If this was more massive, it is nearer to this. If that was more massive, it was nearer to that. And this A is the acceleration of that point. It is the acceleration of the center of mass. So to make this equation absolutely clear to you, external force on a system of masses, then the acceleration of which part? Acceleration of the center of mass is given by this equation. And this may have lot of masses, all the masses together. This acts, the external force on the whole will be the acceleration of system of mass. So say in the case when I am walking over here, then what is happening? I am pushing the ground back and the ground is pushing me forward. What force is helping me to go forward? Friction is the force which is helping me to go forward. Where is the friction acting? On the foot. The friction is acting on the foot. And that F, if I have to put that F is equal to MA, the friction is the only external force. I mean in the horizontal direction. Vertical direction there is gravity, but I am not going vertically. And I have a very smooth acceleration forward. Then what is this M? What is this M and what is this A? This A is not of the foot. This A is at any given point, this is of the center of my mass. That's the acceleration of the center of my mass. So I'll make it quite clear with the diagram over here. Similar to what we made over there, M2, if there is a pull F, then let me write this situation in two different ways. One is, if I consider the whole body as one body, then F is the only external force. Say there is no friction. F is the only external force in the horizontal direction. Then I'll write F is equal to M1 plus M2A, but A of which point? A of which point? A of the center of mass, aCM. So this point will be accelerating with a certain acceleration given by aCM. aCM is given by this equation. This guy will be accelerating with a greater acceleration. We'll have to calculate that. And this guy is going with a lower acceleration. It is hardly getting the force. If say masses were almost same, this is hardly getting a force. So this is say A2 acceleration, this is A1 acceleration. If I have to write the F is equal to ma for this body without breaching this equation will never be breached. It is all correct. This law has been standing for ages now. So if I have to write for this part, then what are the total forces on this part? The spring must be pulling this thing back, because you are trying to pull the string will get extended, it will pull this back. Like a stretched string, it pulls both the ends. So say with the same value, TT, massless spring. So what happens, what I can write for this body is F minus T is equal to M1 A1. That's the acceleration of that body. If somebody was interested in the acceleration of this body, it was not F is equal to M1A, not at all. You had a force over there. And what's the acceleration? So this body doesn't even see that force. What contact force is acting on it is this tension. This has been generated due to that is another story. This body feels that force. So what we write for this body, T is equal to M2A. That's the only force on this. T is equal to M2A. So these are the two equations, which are this A2, sorry, this is for body 2, A2, which are as good as this equation. If I add up the two, equation number 1 and equation number 2, and eliminate T, that is the internal force over here. If I consider these two bodies as one, I get F is equal to M1A1 plus M2A2. That must be somehow equal to this, which we'll be dealing in the next chapter. But these are the equations as they stand. So remember this. Remember this. Whether you know how to get this or not is another story. You can't write wrong equations. If you don't know what is aCM, you can't simply write that the acceleration of this part will be A. You can't write the acceleration of this mass over here. You can't write the acceleration of this mass over there. So you have to write correct equations. Whether those equations are solvable or not is another thing. So that last bit may be a little confusing to you, but all will get clear in a few lectures, because we are going to do center of mass in the next week. I just introduced it, and we can make use of the concept in this chapter also, even though without knowing that we can do all the questions which we'll be doing. But having a look at the center of mass and considering a system of blocks as one, and studying the external force will be quite interesting in many cases, hence mentioned. So don't worry much. The questions are going to follow now, and which is going to make your concept more clear.